Good morning, everyone. Welcome to the webinar on modal analysis of composite beam. There are two parts to the webinar. Initially, I'm going to give a presentation. Following this, there will be a live demonstration showing modal analysis that is done on composite beams using VMAP, how we analyze the data. That live demonstration will be the second part of the webinar. When it comes to asking questions, please type your questions in the chat window. You can do it during the webinar, but at the end of the presentation and the live demonstration, I will answer all the questions that are typed in the chat window. The audience are being placed on mute, so to ask questions, you need to type in the chat window. Okay, let me get started with my presentation. Modal analysis of composite beams. This is the topic of this webinar. Why do we use composite materials when we design structures or components? There are several advantages in using composite materials, but the top two that we would like to highlight here are their high strength to weight ratio and tunable directional properties. Owing to these advantages, composite materials are used as materials of choice in several industries. The key industries being automotive, aerospace, marine, consumer durables, sports equipment such as golf clubs. About the outline of today's presentation, there are two components. One is simulation. In the simulation, we are going to see two case studies. One is that of a cantilever beam. The other is that of a turbine tower. A cantilever beam made of steel is compared with a cantilever beam made of composite. And then a turbine tower made of steel is compared with a turbine tower made of composite. These case studies are illustrated through modeling using finite element method. We do static analysis, we also do modal analysis, and we look at an illustration of the key results of the simulation. The second part of the presentation consists of experiments done on a composite beam. So we perform experimental modal analysis on a composite beam. We do parameterization of the results to get some key parameters such as natural frequencies, damping and mode shapes, and we look at the illustration of the results. So the first part, simulation, the first case study that we are going to look at is a beam made of steel and a beam made of composite. What we have here are the overview of the material properties and the dimensions. The steel, the modulus is 205 gigapascals, Poisson's ratio 0.3, tensile strength 828 megapascals, and density 7,850 kilograms per meter cube. This is a steel beam with dimensions of 600 millimeter, 40 millimeter in width, and 6.5 millimeter thickness. We take a composite beam of similar dimensions but made of an advanced composite system consisting of carbon fiber and epoxy, which gives it a tensile strength of 890 megapascals. So it's technically stronger than the steel beam, which has a tensile strength of 828 megapascals. The modulus is again higher, 220 gigapascals. Poisson's ratio is 0.185. And much lighter, so the density is 1,700 kilograms per meter cube. So given these properties, we can do some expectation on what the results of this simulation would be. But we'll go ahead and look at how the model was set up and also look at the analysis results. So we did a finite element modeling of the steel beam and also the composite beam. We used 3-node triangle elements to develop the mesh for the model of the steel beam and the composite beam. Both had the equal number of nodes and elements. I would like to draw your attention to the dimensions that we saw in the last slide. They are of identical dimensions. So the idea was we take two beams of similar dimensions and apply composite, replace this steel, instead of steel, make it out of composite. And then we look at, okay, is it able to withstand higher load, and does it really have this high strength to weight ratio? And most importantly, we're able to show how to do finite element modeling of structures made out of composites. So this is a simple component, and the key difference between the modeling of the steel beam versus composite beam. Here, I would like to draw your attention to this picture here. There are two layers. Instead of 6.5 millimeter straight thickness, we split it into in equal half. One section which is 3.25 millimeter in thickness, the other half is 3.25 millimeter in thickness, and the fibers are laid in parallel, same direction. So you could say 0 degrees, and both are made of the same material, that is the advanced composite system consisting of carbon fiber and epoxy, the same material properties. So having set up this model, we apply the load to the beam. It's a cantilever. So one end is fixed, and then the tip of the cantilever beam, we apply a vertical load. And when we perform the simulation, given the yield properties of the steel and the composites that we have chosen for this modeling, the load to yield for the steel beam works out to be 405 newtons, and the composite beam works out to be 875 newtons. So the composite beam is able to withstand higher load compared to steel beam, which is really not a surprise. Again, drawing attention to the slide on the material properties, the composite beam had higher strength compared to the steel beam. So this is expected. It's almost double the load that it is able to withstand. And more importantly, it's much lighter in weight. That has significant, that gives it significant advantages when it comes to replacing the material that is steel with the composite. The weight reduction that we get is about 78%. Moving on, we also performed a modal analysis with the same model. The objective of doing modal analysis is to calculate the resonant frequencies and mode shapes for the beam. So what we are looking at here are the deflection shapes corresponding to the 4 fundamental frequencies of this beam. The first mode, second mode, and third and fourth. So the third mode is actually the bending in the XY plane. Something similar to first mode, which is the bending in the ZX plane. So one thing that is missing in the modal analysis that is performed in the simulation is damping. So when we are working with steel beam, steel has a certain material damping. Now when it comes to working with this advanced composite system consisting of carbon fiber and epoxy, the question to ask, is what is the damping? Right? So how do we model damping? It is challenging to model damping for the composite. So how else can we get damping? So we'll see answer to this question on what is the damping that you would use for analyzing a structure made of composite. This is a question that we'll answer towards the later part of this presentation. But looking back at the results from modal analysis, what you are looking at here is a graph which plots the resonant frequency in Hertz on one axis with each of these modes. The last slide we saw the first 4 modes and their differential shapes. Now we are comparing the resonant frequency for each of these modes for the steel beam with respect to the composite beam. So with the composite beam, we are getting higher resonant frequency. In mode 1, the frequency is nearly 120% higher. Second mode, almost similar. Third mode and fourth mode. So what is its implication? For example, this is a structure on which there is a rotating machinery kept, and it keeps exciting it at a frequency very close to the fundamental. What that would mean is the rotating machinery could actually be running at a speed which is 120% higher than the speed at which it could be running when it is placed on a steel beam. So that's the key insight out of these numbers. That's the gain in performance that you can get for dynamic load when replacing material as steel with composite. Moving to the next case study, what we model here is like it's common to make. It's very common to see these structures which are used to hold wind turbines. So there are places where they would use like truss structures, and there are places where these are made of like uniform tubes going all the way to the top. Okay. What we have taken here is not something that is in the field. This is a hypothetical case study where we take a tubular structure. One case we model it as steel, in the other case we replace it with the composite system. Material properties here are similar to what we had used for the last case study. The primary difference here is the geometry. Here we are looking at a tower for turbine, and the height is 50 meters. The diameter is 3 meters and the thickness of 15 millimeters for the tube. And we are using identical dimensions for the steel tower and the composite tower. So looking at the results, again there will be room for further optimizing the structure made out of composite in terms of the dimensions. We are using 3-node triangle elements to model it. There are 7,768 nodes and 15,496 elements. The triangle element, just to get the scales right, we are showing the dimensions of the 3-node triangle element that is used to build the mesh for the finite element model. It's 250 millimeters and 250 millimeters along its 2 of the dimensions, and the third hypotenuse is 250 square root 2 millimeters. An additional level of detail in the composite tower, we are using 4 layers here, but the layers are all parallel, consisting of fibers laid in parallel, and they are all the same material. So we split this 15 millimeter into 4 layers of equal dimension. So each layer is 3.75 millimeter in thickness. If this is the tower, say it is fixed at one end and at the other end we apply a load, the load to yield for the tower made of steel works out to be 1,738 kN, and for the composite tower it works out to be 2,940 kN. An analysis of the strength to weight ratio. Here we are plotting the weight in tons for steel tower in comparison to the composite tower. So we get a 78% weight reduction again in this case. We did modal analysis of this tube. Here when you do modal analysis, the structure is different. In the last case we are looking at a geometry which is rectangle in cross section. Here we are looking at a tubular cross section. What I am showing here is the first mode. In addition to this, when we look at the higher modes, we actually get since it's a tube, you get the breathing modes of the tube. We are not so much interested in those modes, so let's focus on just the first fundamental mode of this structure. So here again, we get a much higher gain in performance. The first resonant frequency for the tube that is made out of composites, it comes out to be 266% higher than the tube that is made out of steel. So I posed this question about how do you model damping for composite beams. So that's open, and we saw how we, using very simple case studies, we just saw it is possible to perform simulation using finite element method to do static analysis to calculate what is the load at which the structure would yield. And we also did modal analysis. But then to do more detailed simulation on that, things like transient analysis, or you apply some kind of stochastic loading on the structure, and you want to characterize the fatigue life and so on. One of the key parameters that one needs to understand is damping. Now, it could get really complex depending on the number of layers that we are using, and since composites can give you a lot of advantage owing to their tunable directional properties, you could leverage them and make an interesting composite structure with multiple layers and the angles in them placed in different directions instead of being parallel as what we saw in the simulation. When the structure gets as complex as that, again, it's more important to understand, okay, how do you model damping really? One of the things that I want to point out here is it's very difficult to incorporate damping in simulation model. So that is where performing modal analysis through experimental methods comes in. So and there are a lot of myths about moment you think of structures made of composites. People have a lot of questions about, okay, this could be really damped. Now, is it possible to measure damping also? What kind of experimental setup do I need? Is it going to be single input, single output, multi-input, multi-output? All of those questions could arise. Now here we have taken again a simple case study, a cantilever beam, and here we are taking a composite beam, and we did a free boundary conditions, and we did the modal analysis of that. The picture shows the composite beam on the top, and then we model it in VMAP to do experimental modal analysis of the beam under free boundary conditions. So what you are seeing in the bottom is the representation of the beam inside VMAP software. The points that are marked in red here, there are like 5 points where we applied vibration pickups, that is accelerometers, and we did a simple impact test, and we are going to look at the results that we got when we performed this experimental modal analysis. After I complete this presentation, I'm also going to show how I'm also going to show a live demonstration of these results in VMAP software. So the experimental setup consists of a data acquisition system, which is 4 channels and with a sampling rate of 50 kilosamples per second. That's the maximum. And we used a hammer to give the excitation to the structure. The hammer has a force rating of 400 newtons and a frequency range of up to 8 kilohertz. And the sensitivity of the hammer is 11.2 millivolts per newton. And when you take the composite beam and give it an impact with a hammer, the beam vibrates, and the vibration response is picked up using a uniaxial accelerometer here, and it has a sensitivity of 100 millivolts per G. All of these details are important because if you are setting up an experiment, one of the questions is, okay, what instrumentation do I need? Now, there are many types. You could be doing a test with a hammer, you could be doing a test with a shaker. Now, you want to know how much force you want to apply. So that would lead you to the next question about, okay, what hammer do I need? What should be its force rating? What frequencies are of interest to you? Now, then the hammer have different sensitivity So on what basis do you select the sensitivity? So I want to bring your attention to this slide to get an idea of some of the numbers that are crucial when setting up the experiment. These are as important as, I would say, the analogy in the finite element modeling is what elements do you use when it comes to meshing it, and how do you set up the boundary conditions. There are various options. So what you pick would make sure your experiment is set up accurately, and thereby your results are accurate. So when you take this composite beam and you give an impact with a hammer, these are the two signals that you would first check well. From these signals, we want to get answers to few key questions. Things like modal parameters is what we want to obtain. So the plot on the top, though it looks like it has nothing at all, essentially is x-axis is time, y-axis is force in Newton, the force with which you are hitting the beam. Very close to origin, there is actually a spike. So that's the impact force that you are giving to the beam. The plot in the bottom is a plot of acceleration of the beam, that is the vibration response of the beam when you hit it with a hammer. It's measured in G. It's plotted as a function of time. So it starts vibrating, owing to some damping, it gradually dies and becomes zero. Now this is the damping that we are interested in. Also we want to know what are the modes of the beam. So from the time signal that we saw just now, we derive some more interesting plots. One of them is called frequency response function. So there are two plots here. The plot in red is a plot of frequency response function. In amplitude, unit is decibels as a function of frequency. The plot in green is coherence. It's a measure of the signal to noise ratio. It tells you the fidelity of the frequency response function, so to say. So wherever there is a peak in your frequency response function, you want to make sure your coherence is close to zero if it is plotted on a log scale. If it is plotted on a scale of 0 to 1, it should be 1. Here it is plotted on a log scale. The units on the left side, that's for the FRF, it's in decibel. The axis on the right side is for the coherence plot. That's going from a negative number to 0 to a positive number. Wherever we have a resonant frequency, this one is close to 0. Here we have it close to 0, and here again we have close to 0. And wherever the FRF draws, coherence also would draw because the signal that is picked up from the accelerometer is really weak. From the frequency response function, to calculate the resonances, damping, and mode shape, we do what is called curve fitting. It's essentially a parameterization technique. The parameters that we want to extract when we solve it are the resonant frequency, damping, and mode shape. So one of the curve fitting techniques that's widely used is what is known as rational fraction polynomial curve fitter. So from the plot, the two peaks, mode 1 and mode 2, have a resonant frequency of 399 Hz and a damping of 50.64. It's given in Q factor. Then the second resonant frequency is 1102 Hz and a Q factor of 45.34. So what does this mean? At that mode, the beam has a particular mode shape, like a bow. Then the second mode, it has this next higher mode, which essentially consists of 3 antinodes. So in summary, what we saw in this presentation is how to perform modal analysis of composite beam through simulation method and experimental method. Needless to say, composites give several advantages for a structural designer owing to their high strength to weight ratio and also tunable directional properties. So when it comes to finite element modeling, we saw how we set up the material properties, how you could have like layered composites, how you set them up, how do you set up the boundary conditions, how do you apply the load. And as expected, we got results which are in tune with, we demonstrated that the composite beams are able to handle higher loads though they are lighter in weight. And for dynamic loads, given that the resonance frequencies appear at much higher values compared to the beams that are made of steel, what that means is you could be putting, say, rotating machinery or any kind of exciting loads which could be operating at higher RPM or higher speed, and which has its own advantages. Now I want to move to the second part of the webinar, which is the live demonstration of some of the results that we saw, especially to answer the question about how you measure damping for composite structures. So I'm using VMAP software. VMAP is vibration measurement and analysis package, and you can do experimental modal analysis and analysis of the experimental modal analysis results and correlation with your final element analysis data. So this is the representation of a composite beam, and there are 5 points, 1, 2, 3, 4, 5. They are marked in red. At these points we placed accelerometers to measure the vibration response when we give an impact to the beam using an impact hammer. So this shows the complex mode indicator function. It has picked up 3 resonance frequencies. So I'm using rational fraction polynomial curve fitting to calculate the resonance frequencies, damping and mode shapes for the first resonant mode. The first mode, the plot in red is measured data, and the plot in green is what you get after curve fitting. This gives the resonance frequency and Q factor for the first mode. Likewise, we can repeat the procedure for the second mode. Error and curve fit amplitude to overlap this flash. So the plot in red is measured data, and the plot in green is what we get from curve fitting. This gives the estimated resonance frequency, estimated Q factor. There is also a multi-degree of freedom curve fitting. So what I just did was I took this plot, which is in red, which is the measured data, and I'm using VMAP to fit a mathematical model where there are 2 resonance frequencies. As you can see, there is a very perfect fit curve that we have obtained. It's right precisely on top of the original data that we measured and that we started on with. So when you get that kind of a fit, the accuracy of the results that you get for modal parameters, that is resonance frequency, Q factor, and mode shape is very high. Now let's move on and look at the third modal parameter, which is essentially the mode shape. So this is a free beam, and this is the mode, this is the second mode that we are looking at. In the next higher mode. Okay. So it's summarize what we saw in this live demonstration, we took a beam that is made of composite. We hang it from bungee cords at two ends to simulate free boundary conditions. Then we give an impact to the beam and we measure the response at various points. In this case, we measured at 5 locations. Then with the experimental data, we did curve fitting to get the modal parameters. One step that I have not shown here is correlation with FEA. So in this case, we don't have it. But there are examples where it is possible to look at the correlation as well. That brings me to the end of this presentation. Thank you for attending the webinar, and please type your questions and we will answer them. Okay, one question that has been asked is what is the, how do you, you mentioned about correlation and can you explain a little more about correlation? Okay. When I'm talking about correlation, essentially it's about comparing your finite element analysis results of modal analysis with experimental modal analysis results, which is key. Especially for people who are doing, it could be on either side of the story. You could be somebody who is into testing alone, or you could be somebody who is doing finite element analysis alone. So there is always a question about, okay, how do I know if my results are right? So especially if you're doing simulation, it's important to take the test data with the prototype and do correlation. So talking about correlation here, there are several metrics to capture correlation. One of them is MAC, Modal Assurance Criteria. There are other metrics also. In the examples that I showed you, I either showed the simulation or the testing. But there are case studies where we have been able to take the test data and look at the simulation data as well and calculate the MAC. The MAC is plotted on a scale of 0 to 100. So if you have 100, that is good, a perfect correlation. If it is 0, there is perfect lack of correlation. Another question is this, VMAP or finite element analysis software? The answer is no. VMAP does three things. One is experimental modal analysis. Two is analysis of experimental modal analysis data. That is, once you have experimental data, analyzing it. Third, it can be used for correlation with finite element analysis results. The finite element analysis could be any of the commonly used FE packages, ANSYS, Nastran, Abacus, now it's called Simulia, Radios. You can import your finite element models built in Hypermesh. And with that, you can, and once you have a physical prototype, you can map out and measure experimentally. So in that sense, it links to different data acquisition hardware for doing experimental modal analysis. As you may know, experimental modal analysis is done in many different ways. The example I showed was done with an impact hammer. You could do it using a shaker. There again, when you use shaker, there are different types of signals that are used to excite the structure. Then there are different, depending on the number of sensors, the number of exciters you are using, you could have MIMO testing, CMO testing, single input multi-output testing. Then analyze the data and also compare it with your finite element analysis results. So all the registrants will be getting an email from us to get your feedback, and along with it, you'll also receive a link to the video of this webinar. There are no other questions. We are going to close the session now. Thank you again for participating in the webinar. And as I mentioned already, you will receive an email with two things. One, feedback form, and we would appreciate if you could fill in and send us the results. It'll help us in terms of the future webinars, and also a video that you can download, and that would be a recording of this session. Okay, there has been one question. We'll send you an email. The question is, if we do experimental modal analysis, how we design extract location for component impact hammer. In short, VMAP, for example, has a module called Test Planner, which allows you to do that precisely.